So, are there any questions with the first round of the rational class? Maybe some feedback, some things to be fixed. I'm a little more particular about this one because you're using it for a couple more projects, so you've got to get those pieces together and meet the kind of the specifications that I'm after there. Anything with the rational class? Anything with the integer set? I pretty much got through that, right? I think I covered everything I needed to cover. Okay. Anything you'd like me to review with that? Clarification? So again, what I'm really after seeing in the integer set is the use of logical operators to perform your set operations. So ors to do union, ands to do intersection, you know, we could use nots to complement. I don't have you do a complement set. I should maybe have you do that, but we don't need to. And think how you might. I don't think I described subset. Think how you might be able to test the subset. All right, as a combination of intersections and intersections and unions. Think how you might be able to implement that with your already existing operations. Much in the same way with the rational, I had you do negate and add to do subtraction, reciprocal and multiply to do division, those kinds of things. So, anything? No? Good. Right. So what I'll do is, I know I'm kind of getting ahead, but for those of you who are, have absolutely nothing else to do, you got all your work done over break, and your integer set's off the table, and you want to move on. The next project is coming back to the overload of the rationals, where we are going to look at a nifty feature of C++, where you can overload existing operations. So the idea then is that we can have rational ABC, all right, and then in our main program we can say C equals A plus B. That we can actually use the arithmetic operators as if these objects are numbers, which they are, right? So we can overload. So this is the chapter on overloading, a couple chapters on overloading. So you say C equals A plus B, C, and then you can, still C print. Right. C equals A minus B, C print. Right. You can go so far as, maybe I have D, I can have D equals A plus B divided by C. So this system is set up such that the compiler will apply the precedence rules as already hard-coded into the language. Change that. Addition and subtraction will be done after multiplication and division. If you need to override it, you can use parentheses. All you have to do is overload what does plus mean, what does minus mean, what does times mean, what does divide mean. You're overloading. You are going to supply to the class what these will be interpreted as. Right? So we're going to be able to say that we can add two rationals. We can subtract two rationals. then we can multiply two rationals and divide two rationals. All right, so we're able to specify that. Further, if you wanted to, and you don't have to do this, but just to show you that this could be enhanced in a significant way, we could say I could take a rational and add an integer. You could actually say, oh, I could have as a second argument to the plus sign, I could add an integer to that, which is what? That's easily interpreted. The integer is simply the numerator, and the denominator would be a 1. So it would be very easy to say I want a rational plus an integer, and similarly do that the whole way down. All right. Flipping it so that the integer comes first is a little bit more challenging. Right? Basically to allow any combination of rationals and integers to be mixed. But think about it. The compiler handles this type system. You can switch the order of doubles and integers, right, throughout your program. You're not restricted in any way. All right. To allow that to happen with your new number class of rationals would be a little bit more challenging, but you could do this. I'm only interested for the moment, though, is in that you just implement the addition, subtraction, multiplication, division of a pair of rationals. Okay? So in your application program, you have now the liberty to express your arithmetic operations in a very normal way. You don't have to use this dot add, dot subtract, dot negate, whatever. Okay? In fact, I do want you to implement the negate so that you can say d equals minus c. You should be able to do that. Or reciprocal. I think I defined reciprocal. I can't remember what character I said you would overload for reciprocal. Exclamation point? Okay. It's a little unconventional. Okay. I have to use, I can't pick an arbitrary character off the keyboard. I have to use a pre-existing operator. So that's a not operator. So it's kind of close. Reciprocal, not, kind of close. It's a unary operator. You negate a single value. You reciprocate. Is that a word? You make it a reciprocal of it will be of a single rational. All right. That's the overview. Okay, so far? Now let's look at some blurry details. Right, so to express the overloading, right? So if I want to implement the fact that I want to add two rationals, all right, so that I can say c equals a plus b, all right? What I need to do is define in our rational class a method. It's rational. All right. Now these can't be void. You have to make it return a rational. You must return a rational. All right. The code to indicate that we are now overloading the plus, you say operator plus. I'm running out of board here, and you pass one parameter, rational. Okay. So that's how you specify the overloading. This is the overloading of a binary operation. Add, subtract, multiply, and divide are binary because they take two arguments. Something to the left and something to the right. The right hand, it's the right hand argument that is the parameter. The left hand argument is the object. All right. So this is syntactically, when we say this is natural. You've been programming with this notation forever. Since you have entered your programming life, you've been programming this way. But this is really C equals A dot operator plus B. Right? You can write this or you can write this. Okay? I tell you that because this is what you have to implement. This is the method you have to implement. All right. But when you write the infix operator plus, you're really actually calling this method. That's all. Right? If I would say D equals A plus B divided by C, basically that would be A dot operator plus B dot operator divided by C. And assign it to T. Right? So when we write this is in fact the equivalent code that C is generating in terms of method calls. So when you supply an operator plus, you are now overloading the plus sign, and the compiler will be all able to deal with that. Okay. So what does the code look like? Well, it's now taking the form of your add. You've already implemented add, haven't you? Right? Don't reinvent it. Don't copy the code. Call your add method. Okay? So, you can say rational, I have to think about this. Rational, and then I may be slightly off, and you'll just need to look in the book for the pattern here. Declare a rational temp equals, let's see, how do I want to do this? This, and is that what I want? And then temp dot add. So if I pass in C, add C. Yeah. Return. That's roughly what you're doing. So grab this, which is A, and temporarily store it. Call your simple void method, add C to it, and return temp. Okay? So, again, we're leveraging the fact you already have taken care of how you add two rational numbers. Right? And that's taken care of here, and your adding of rational numbers should take care of the simplification, and that's it. Subtract, call the sub method. For multiply, call the mult method. For the divide, call the div method. For the negate, by the way, unary, this is the pattern for binary operators. You pass one parameter. The other parameter is this. Right? A is mapped to this B is mapped to C, and you've got both. Right? If C equals negative A, then that is actually equivalent to C equals A dot operator minus with no parameters. Right? That's the unary negation. Right? If I want to just say negative A, negate this rational number is really calling this guy. And the distinction between operator minus with no parameters and operator minus with one parameter is the fact that one is subtraction and the other is negation. Okay? So you would have rational, colon, operator, minus no parameters. So for binary operators, you pass one parameter. For unary operators, you pass 0 parameters. Okay? And it's because you're using this. And so you can basically, I don't know if you can get away with return. I'd have to try this out. I haven't done it lately. Return this dot negate. It should be that trivial. Something very close to that. You can overload any C operator. Plus plus, minus minus. Do you realize that when you say C out and use the less than signs, that's an overloaded operator? That's really, in the original language, that's a left shift of bits. Take the bits, shift it to the left. So when you say C out X, whatever X is, if X is a double, this has been overloaded to take a double parameter. If it is an integer, it's been overloaded to take an integer parameter. If it's a character, it's been overloaded to take a character parameter. If it's a string, it's been overloaded to take a string parameter. The overloading of less than is pretty significant. And if you didn't realize it, in the original C language, that's a left shift, which says take the bits and shift them to the left however many positions the argument is to the right. We just never use it. So the writer, the creator of C++, cleverly reused this operator less than in input-output context. And that's pretty much 99% of the time that's what you see. Questions? Is this making sense? It's there are great examples in this book to see how overloading is done, and I certainly recommend you reading that very carefully and following those patterns. You don't have to overload input-output. You're welcome to do it. Wouldn't it be cool to say C out, C? Call your one of your print functions. It's doable. You can provide direct output of your rational class. You are also, so this is so trivial, right? You also now have to implement the comparison of two rational numbers. Okay. Any questions before I erase this? Make sense? All right? Yeah? No? Anything you'd like me to back over? Anybody? So, if I want to compare, so if I want to say if A is less than B, right, so I have to overload that. So I would have Boolean rational operator less than rational. So if I want to overload the less than sign, then it's operator less than. But it's binary because it takes two parameters. I need to pass one. Okay? Now, if A is R over S and B is T over U, to compare two rational numbers, please don't divide R by S and T by U. When you go to division, you don't get an accurate answer. If it's 1 over 3, you get 0.333333333. Lots of threes, but it's not perfect. Okay? And to compare imperfect numbers is a bad idea. Numerically. Do not compare equality. Right? So what you best do is cross multiply. Compare. Now you're comparing integers. Perfect. No loss of precision. If you compare the floating point equivalents of these things, you are introducing imprecision. You don't want to do that. When you compare by the cross multiply, you stay in the integer number system, and it will be exact. So please cross multiply. So when you compare A and B, all right, it's A's numerator times B's denominator less than B's denominator times B's numerator times B's numerator times A's denominator. So I'm looking at the positions here. Make sense? All right. Again, minimize the copying of code. All right. I would like you to note that A less than B. All right, let me do this. A greater than or equal to B is equivalent to the negation of A less than B. So you do the work, you do the coding to implement less than. The implementation of greater than or equal is simply the negation of less than. Done. The logical negation of less than is greater than or equal. Yes? Okay. Similarly, A greater than B is equivalent to not A less than or equal to B. A not equal to B is equivalent to not A equal to B. Yeah, that makes a lot of sense. So I should only see cross-multiply code in 3 instances of the 6 relational operators. The other 3 relational operators should be the negation of a call to 3. I don't care which 3 you choose to negate or implement, but I do want you to, just simply implement the cross-multiply in 3 of these, and then use the complement of the other 3. Yeah.
For the equality comparison, can't you just compare directly?
You can, yeah. Yeah, you could just compare the numerator to the numerator and the denominator to the denominator, providing they've been reduced. Yeah, sure, safe thing. Yeah. That would be true. Yeah, just it would save the multiply, but probably for consistency, I would just go ahead and cross multiply. The other thing is, if for some reason you have a flaw, for some reason simplification didn't happen, this will still work. That's the other thing. I think those are the operators, right? So the 4 add, subtract, multiply, divide, reciprocal, will be implemented as the explanation point. It's interesting, you do have the option to say that exclamation point returns not a Boolean, but it will return a rational, the reciprocal. You can't change the precedence rules. You can't say, I want multiplication to be done after addition. You don't have that option of changing the precedence rules of the hard-coded operators. But you do have the option of deciding what is computed with those operators. In this case, add is now going to return a rational number. You don't have to implement increment, but if you kind of get on a roll and think this is really cool, you can implement as many of these operators as you want that make sense. With rational, I suppose you could add one, subtract one from its value. That could sort of make sense. If I'm going to invest any time, I would implement input output, at least output. And it might be a good exercise just to say, hey, that's doable. There's a good always. The reason I chose this book is that it's got good examples. I still go to it on very often to say, let's see, how does this work, and I can pick out an example. So, questions? So that's the overloading exercise, and once you kind of get one of them working, the rest of them will fall into place. Should be fairly straightforward then. Let me know if you run into any snags. Next week I will then talk about the shapes hierarchy. That one may take some time. All right. Questions? All right, so that'll be it for today.